Example 14.6 is going to be very similar to example 14.5. It says, find the zeros of the polynomial function given and state the multiplicity for each zero. The only thing that we don't have here in this example is the linear factorization. We'll revisit linear factorization in section 15. So for now, let's just focus on finding the zeros. So when you take a look at f of x, you again are probably going to want to attempt factoring by grouping, because it doesn't say how to find the zeros, it just says find the zeros. And if I can do factor by grouping and make it work, then that's going to be the fastest way to finding the zeros. But as it turns out, if you attempt to do factoring by grouping, it is going to fail. So I will make a note here that factoring by grouping fails. So since factoring by grouping fails, I want us to attempt the factor theorem, because we have to have a factoring of our polynomial in order to find the zeros. So the factor theorem states that we are going to want f of x divided by x minus c in conjunction with the remainder theorem, and we are looking specifically for a remainder of 0. So I need a list for potential values for the divisor. That's going to come from our p over q list. And just like with example 14.5, I'm not going to show all the details about how to find the p over q list. I'm just going to give you the p over q list so that way we can move on with the rest of the finding of the zeros process. So we're going to have plus or minus 1 as well as plus or minus 1/2 for our p over q list. And we are going to be expected to choose one of these to perform division with. We're going to use synthetic division, and my coefficients are 2, 1, -3, and +1 for the dividend. I always bring down that leading coefficient, and I want us to try one of these values. I'm going to pick 1/2, not because I know it's going to work, although I do know it's going to work. I wanted you to see how a fraction behaves as we choose it for a divisor. You're still just going to do the same multiply and add process. It's really not going to change anything, but I know some of us have a fear of fractions, and so it's good for us to get over that. So let's see what happens here. 1/2 times 2 will get 1, 1 plus 1 to get 2, 1/2 times 2 to get 1 again, -3 plus 1, -2, 1/2 times -2, -1, and then we add there at the end and we get 0. So that's what we're looking for. That's our remainder. That tells us that f of 1/2 is equal to 0. And then we also have, of course, the quotient over here. And the purpose of the factor theorem is to simulate factoring. So now we can say that f of x is equal to the divisor, which is represented by x minus 1/2, multiplied with the quotient. The quotient will be represented as 2x squared plus 2x minus 2. And once I initiate the factoring process, like I have here, I will then go back and think about other types of factoring techniques that would apply. For example, greatest common factoring. Don't forget that real simple factoring technique, GCF. I can factor out a GCF of 2 from the quotient. So this would give me f of x equals 2 times x minus 1/2 times x squared plus x minus 1. And then I might think about trinomial factoring on x squared plus x minus 1. Unfortunately, you are not going to get very far if you're only using integers, because the only way to really be able to multiply to get -1 is to have 1 times -1. But then if you add 1 plus -1, you're going to get 0, but we were kind of hoping to get a +1 there. So that's not going to be a very good option for us. So I'm not going to worry about trying to do any trinomial factoring. So this is going to be as far as we can take the factoring of this. So now let's go ahead and do the finding of the 0 step, which is to let f of x be equal to 0. So any of the factors that are not a constant, I will set equal to 0. So that would be 0 equals x minus 1/2, or 0 is equal to x squared plus x minus 1. The first factor of x minus 1/2, when we set that equal to 0, this is going to give us some redundant information. We already know that 1/2 is going to work. The synthetic division told us that. So this is just going to reiterate the fact that 1/2 is supposed to be one of our answers. Now, with 0 equaling x squared plus x minus 1, there are two options for solving that. Factoring is not one of them. We've already said that trinomial factoring is not going to work. So your other options are going to be complete the square, which is something we discussed in section 12 when we talked about quadratic functions and vertex form. Or you can use the quadratic formula. This is the perfect setting for the quadratic formula. So that's what I'm going to use. So we'll set this up, x equals negative b, so that's negative 1, plus or minus the square root of b squared, so that's 1 squared, minus 4 times a times c, so 4 times 1 times negative 1, all divided by 2 times 1. And I would encourage you to work through the quadratic formula yourself before getting to the answer here on the video. I will go ahead and finish working this out. We're going to end up having negative 1 plus or minus the square root of 5 all over 2. So this tells me that there is two answers because of that plus or minus, and the square root of 5 is not going to simplify, so there's no reason to even worry about dividing by 2 either. So here's our answers. We have x equals 1/2, negative 1 plus the square root of 5 over 2, as well as negative 1 minus the square root of 5 divided by 2. And these all have multiplicity of 1. That's all we were asked to do, was find the zeros and state their multiplicity.